Here let's consider the concept of hydrostatic equilibrium. Consider the Euler momentum equation. It says that d by dt of the velocity u plus u dot grad u is equal to minus grad p over rho, and this time we're going to include a body force from gravitational potential, g. If we want to consider a first solution to the system, we might consider the hydrostatic equilibrium solution, which says hydrostatic u is 0, and equilibrium d by dt is 0. That means this equation goes to 0, and this term goes to 0, leaving the balance that grad p is equal to rho times the gravitational acceleration vector, g. This is hydrostatic equilibrium. This is not a solvable system. We have two variables, p and rho, and we have one equation. So we have two variables, one equation. We need something that links p and rho if we want to solve this. We need an equation of state or something similar, and we'll need, as we see, a further step as well. Let's start with an equation of state we'll use quite often. Let's assume an ideal gas. An ideal gas has an equation of state where the pressure is given by the density rho times the gas constant times the temperature. And if we plug these into hydrostatic equilibrium and we rewrite hydrostatic equilibrium in a clever way, then we get that grad p divided by p, which happens to be the gradient of the logarithmic pressure. That's just from grad p over p is grad log p. That's true for any system, is equal to g vector over r times t. This is the general hydrostatic equilibrium for any ideal gas. Hydrostatic equilibrium for ideal gas. Now you might ask yourself, what have we gained by rewriting the system in this way, and in particular in introducing t, which we don't know, when we also have p, which we don't know? We still have two variables. We still only have one equation. What gives? Well, quite often we can make a good guess for what the structure of t of z is. Often we know the vertical structure of z, or the simple structure, the vertical structure of t, of temperature, from considerations of the thermodynamic equilibrium. To understand this in more detail, we have to have a temperature equation, a partial differential equation for t, which we'll see sometime soon. But for now, let's just recognize that if we have an equation like that, we can come up with some simple equilibrium profiles for t, maybe more easily than we can for the pressure p. And if we know t from thermodynamic equilibrium, then we can calculate p from this relationship, that grad log p is given simply by the gravity vector over RT. The simplest such equilibrium is the isothermal atmosphere. So our sort of first approximation is isothermal, which means that t is just a constant. Well, if t is a constant, then grad log p is g vector over r. T is a constant, which is minus g scalar over r t z hat. which we call this combination here the density scale height h rho 1 over. So this is just minus 1 over h rho z hat. I drew my rho a little high there. This is a subscript rho rather than a multiplied by rho. It's a subscript telling us that the scale height we're talking about is the scale height that relates to the density of the atmosphere. So I'll put that as a subscript. So the solution to this is if h rho is a constant because g is a constant, t is a constant, r is a constant if we assume that the gas in the atmosphere is well mixed. And then this is a simply integratable system, and we get that log p is equal to minus z over h with some integration constant. And then we can solve this to get that P is equal to some base pressure, some P naught, times E to the minus Z over H rho. This is our exponentially stratified isothermal atmosphere. That's our simplest system that we tend to consider, and that's relevant to astrophysical or atmospheric systems. Now, the next simplest system, the next level of approximation, we said previously that T was a constant. So the next simplest is to say that instead of T being a constant, that the gradient of T is a constant. That the grad T is a constant rather than T. That means that T is equal to some base value plus this constant, let's call this constant beta, just for simplicity, plus beta times Z. And this is a linear profile of temperature. Beta is some constant, Z is our height, and so this is an atmosphere where the temperature changes linearly with height. This class of atmospheres is called the polytropes. Polytropes. And these end up being extremely good descriptions for Earth's atmosphere. Good for planetary atmospheres. They're also good for the interior of the sun and places where you know something about the overall structure, driven especially by instabilities like convection.